Okay, so let's start our session today. As I mentioned, um, on its learning, I decided not to upload the notes or the video, just to give you instead kind of a write-up about kind of a summary what we saw last class. Okay, I think that will be more effective, and I hope some of you have read it at least to prepare for this class, the continuation. But I just wanted to go through we had some difficulties last class, so let's see. So one thing was when I was trying to calculate, so the whole point of the calculation was to show you that even though hydrates, they have a high proportion of water and a low proportion of hydrocarbons, they still store quite a significant amount of methane, a significant amount of hydrocarbon. Okay, and I did the calculation here, like you get 7.53 kilomoles of methane, and that corresponds to the same amount that if you have to save the same amount in a cubic meter as what you have in a hydrate, you'll need to compress it to 180 bar. Okay, so keep that in mind. It has a low hydrocarbon content, but it's very significant. So that was one thing, and I think I did kind of a mess while doing that calculation in class. Then, so here you have, that's actually data taking from an exercise that the last group, I think 2 years ago, did. Okay, so I just took that's pressure and temperature, the phase envelope, and you had, that's actually Snøhvit. You will do the same calculation now in exercise 4. The pressure and temperature at the inlet of the pipe and at the coast where you have the LNG processing plant, and at some point you cross the hydrate formation line. So from that point you have risk of having hydrates. And also these are also data taken from the same example. What happens if you add now an inhibitor, in this case methanol, that the line goes to the left. I think I did it, but with much less professional. And there was another thing missing that I did the calculation. You got, I think we got $130,000 that you have to spend by day. But remember, we don't just dump all of this MEG into the sea. Okay, we just recover it. So a big part of that MEG that we are injecting, we're recovering. So that has to be an initial investment. But later you just have to make up. You all the time are going to lose some inhibitors, some methanol, but so you don't have to be spending that money every day. Okay, but rest, I think the numbers were okay. Yeah, slug flow, I think we didn't have much to say, but I just put a kind of a sequence of the picture showing the accumulation. Scaling, I think we didn't have much to say. 2 types, reduction of pressure and temperature, mixing of water. There are also different types, more exotic. We are just going to cover the basic. Yeah, maybe I have some nicer pictures. The thing is that before class, exactly before class, 5 minutes, I lost all the images. Okay, so I had to do in these 5 minutes to go and search them very quickly. So that's why here I have more figures than what I had the other day in class. So that's the problem when all the time when the computer asks you, do you want to overwrite the file? You have to think very carefully. Is it the same file or is it a new file? So I just say yes, and then the file was empty and big chaos. I'm sure it has happened to you. So erosion, we also saw erosion. I'm not sure if I put that name, but there is a practice from DNV, the Noshke Veritas, and they give for some components that we already know, like bends, like pipes. They already have some calculation methods what is the minimum velocity or what's the maximum velocity that you can have in the component, depending on the amount of solids that you have and depending on the resistance of the material. And that number is RP 0501, recommended practice. And but there are some other components, like when you have, for example, boosters, when you have, for example, chokes, when you have, for example, manifold geometries, that they are not so standardized. So for that case, you use computational fluid dynamics, CFD, and that basically consists on you try to calculate velocities 3D in the domain, and you try to detect where you have high velocity areas, so that's where you will have most likely erosion. And then with that, you try to compute also the velocity of the fluid hitting the wall and the angle. And with that, you can compute the erosion rate, and then you can see if you have to change the geometry to get a smaller erosion rate, or if you have just to limit the rate up to a certain value. So that's something that is done in design. And so in design it's nice, you can change all the diameters, you can change pipe diameter, etc. But when you are already in the production, in the operational phase, you cannot make those changes that simple. Okay, every change is a big investment. So sometimes when we have, for example, more production of sand than what you expected, and that's a very big unknown, sometimes the only solution is to lower the rates, the production rates. Okay, let's say you plan to produce 10,000 barrels of oil per well, but then you see that that gives you excessive sand production, that will give you excessive erosion, that you will have a leakage of an integrity problem in a pipeline. So then the only option is to reduce it. Sometimes you say, okay, maybe if I change this component, then I will have less erosion, for example, in that component. But if it's in a pipeline, in a big part of the system, then the only option is to reduce the rate. Corrosion, some picture, I think that picture was not last class. And corrosion, just to make you aware that not only is every time that we have contact between the metal and the water, but also it can happen very strangely in gas pipelines, transport pipelines, when you have condensation or you have splashing of liquid on the top of the wall. And that's top of line corrosion, yeah, TLC. And measures, basically you can use a very resistant alloy, a metal corrosion resistant alloy metal, that you mix the carbon steel with some other things that make it more resistant and less reactive to water. But also you can put inhibitors that basically they try to isolate the metal from the water, okay, the metal from the liquid. And some methods used for that, inhibitors, they have these chemicals that they have long tails. One part attaches to the wall, and the other part is like keeping the water away with these long tails. And the other thing is that you can create some rust, you can create some oxide that is not going to be reactive. Okay, it's going to form a protective layer, and after that it's going to remain inactive with the liquid. Okay, so that was kind of a big success some years ago, just by using baking powder. You put it in the pipe and you create this layer. Okay, was some guys make a lot of money. Then wax, here is the line that I told you, also more professional. I took some from some journal, and you see it has a small inflection in the, and these are wax crystal. I think that figure I showed before. You have two things: wax wax appearance temperature, or also called cloud point, and you have pour point. Okay, pour point, when you turn the jar, it doesn't flow. And and here we had a question that, okay, that, what is that? Is that wax or is that asphaltene? Okay, last class. And like I told you, wax and asphaltene, they are really like cousins. Okay, the main difference of asphaltenes, wax is like long alkane chains, okay, that they are mostly linear, and they are purely very heavy hydrocarbon chains, but they don't have much more than hydrocarbons. While asphaltenes, they have this cyclic structure, okay, like benzene. They have hydrocarbons placed in like in a cycle structure, and then you might have double bonds between the carbons. And I think here we have, I pull a picture from okay, how it looks like. Alkanes will be waxes will be much more linear, and that's an asphaltene structure, molecular structure. And another thing with asphaltene is that it has sulfur, it can have nitrogen, oxygen, and can also have some heavy metals. But going back to the question, so here you have really like a mixture of asphaltene and wax. Okay, the main thing is that waxes, they precipitate and they try to join or grow around asphaltene particles that you have in the fluid. Okay, so all the time when you have waxes, you usually have asphaltenes, and they help on the nucleation process to grow these wax crystals. But they are very different on appearance. Okay, wax is very pasty. It's like just like a wax, like candle wax, and asphaltene is more hard. It's like coal. Okay, you can see some picture. You can scrape it from the pipe, and it almost becomes like a dust. Okay, so they are very different, and it's true what Statu told you, that you have here asphaltene, but it's mainly wax around asphaltene. Okay, so a very big difference, and they're very different also visually, but they are like from the same family. And asphaltene, they really are a major player in wax deposition, just to help the growth. Yes, there was one more thing. No. Yeah, then we came to emulsion that I have to make a bit quick. So emulsions basically is a very fine and very stable also. The main characteristics of emulsion is that it will remain stable for long transportation distances. Okay, or for long periods of time. Like in this case, we mixed these two, oil and water, in a blender, and it gave me that looks like almost like a mayonnaise or something else, and that will become stable. That took like a day to separate afterwards. Okay, so you can see more or less the time scale. But the main consequence is that if you measure, I think that also that figure I put, but by hand, now you have it a bit nicer. If you measure for the same rate, total rate, okay, oil plus water, but you measure the delta P, you will see that if you change the percentage of water, the water volume fraction, that is Q water divided by Q oil plus Q water, you will see that it starts to increase until it reaches a maximum point, a point of maximum pressure drop, and then again starts to decline. Here you have pure water flow, and here you have pure oil flow. So that you have to be very careful on the pipe, because that can be very significant. In this case, it's just 2.5 times, but it can be all the way to 10 times. So if what you expected, you did your calculation, you assume that, for example, you were going to be down here, and then all of a sudden you got a very huge pressure drop, your production first will be reduced significantly, okay? And maybe some equipment that you had designed for pumping at a certain viscosity won't work appropriately. Okay, pumps usually, when the viscosity of the fluid increases dramatically, the performance of the pump also declines dramatically. We are going to see later ESPs, but it's a big impact. So people, what they do, they say, well, oil and water, they behave like a mixture. Okay, they behave homogeneously, so I can calculate just with a single flow, single fluid incompressible equation. Okay, the density will be the density of the mixture. If you remember, we have already seen that formula before. So that's for emulsion. That is rho of the mixture equal to rho of water times alpha of water plus 1 minus alpha of water rho of oil. Okay, but the viscosity, we have a certain viscosity of the mixture that we can back calculate from that plot. Okay, from that plot I can say what will be the density or the viscosity of the whole mixture to have the same pressure drop. Okay, and you get a chart similar to that one. Okay, and then you can define an expression of viscosity of the mixture versus the water fraction. Okay, and in this case, that's a guide. There are many expressions. Another one that is used is forgot the name, but there are many others that are very famous. But basically here I'm tuning it to an exponential. Okay, I have a base value here, and I have an exponent, a coefficient that multiplies the exponent. And if I have some measurements done in the lab, I can exactly match my behavior. Okay, and that's what I use when I want to calculate pressure drop in pipe. And the management, well, we have demulsifiers, everything that prohibits. Okay, so maybe I mentioned it also last class, but just to refresh it, what happens here is that you change from a water in oil dispersion to an oil in water inversion dispersion. Okay, you change when you go from the inversion point, you change from that to that distribution. Okay, and that was all. So I hope you read it. So now let's have a, just like to wake you up and to wake myself up. Let's see, we can make a Kahoot. Yeah, let's see. Okay, so where are my Kahoots? Okay, so let's usually the music gives some just to check if you read wall colder than the fluid. Okay, remember for hydrates we need three things. Okay, we need to have liquid water. Okay, we need to have free water, what we call free water. We need to have also a particular combination of pressure and temperature. If you remember on the hydrate formation line, our envelope P and P, we are only going to have hydrate formation inside that region. So only if we have a certain combination of pressure and temperature. And the last thing is that for hydrate we need also small hydrocarbon molecules. Okay, less than, and that was in the text, 9 Armstrong. Wax colder than the fluid is for which problem? For wax. Okay, wax also we have to be inside the region, and yeah, we So let's see if that comes next. Okay, that one did a bit better. Um, so basically the main effect of tech is that you try to reduce that region, okay? And it does it by avoiding that the molecules of water will position themselves in that special configuration that gives hydrogen. Okay, so the two things are really okay. Slow down the cooling. You know, unfortunately, we don't have any chemical that is doing that. Okay, that allows to do that. That's something the industry some have looked into. But the only way to slow down the cooling is just to improve the insulation or to really to create to use heat tracing. Okay, and the deposition of waxes tech has nothing to do with waxes. Okay, still the same, guys or girls. Okay, 1 and 5. Okay, that was a tricky question. Okay, why? Hmm? A trick question. Okay, remember we have two types of slugging: severe slugging and also hydrodynamic slugging. Okay, I think you haven't read yet the. I can see that there was some miscommunication. Okay, we have two types. One of them is hydrodynamic, and the other one is terrain or severe slugging. Okay, severe slugging, it causes by accumulation, the profile of the pipe. If you have a riser, basically because of accumulation of liquid, the pressure of the gas builds up, and then it has to blow in creases, and then it blows everything downstream. While hydrodynamic is something that, if you have certain conditions, no matter if which pipe will, you need the inclination of the pipe, but if you have certain fluid properties, certain superficial velocities, it occurs naturally. Okay, it's like a dynamic configuration, equilibrium configuration of the fluid. Okay, it's just by so that's what this diagram is giving us. It's the flow pattern, and it tells me if I go in 5 and 1, I will have hydrodynamic slug. Okay, not terrain-induced slug. So that was kind of a trick question. Okay, let's see if that changed. No, it didn't change at all. That one I got you really bad. Huh? So that's also another trick question. Experiments, they are actually also relatively, in multi-phase flow experiments, they are relatively expensive to make. Okay, and also you want to make it in big pipe size, because I told you the experiments that are done in 2 inch are don't scale very well when you go very high. Okay, 8 inch, 10 inch, but they are expensive. Okay, so really in field design, we usually use these simulators. We use Olga, LEDA, Flow Manager, okay, to see if we will have slugging. If we see that we have a very challenging situation, like we have long transportation distances, we have potentially problems of liquid accumulation, we have this riser configuration, and we think that the models are not predicting very well, then in that case we might commission some like this exercise 3. Oh no, it was exercise 1, was it? That you have this issue that the flow assurance expert said this is not good, okay, for our particular case. If you feel like they are not good, you have a particularly very challenging case, you might commission experimental studies. But this is not very common, okay, because they are expensive. They cost money, they have to be done in large scale, and really it's only if we have a very challenging situation that we use it. Okay, we didn't change much the remember we have two main types. There are many other types, exotic, but two main types: carbonate and sulfate. Remember, sulfate all the time is because of sulfate in the seawater. So that comes from injection. Okay? When you have mixing of water from injection. Uh, carbonate, uh, CO2 dissolved in the water, and then you have calcium that comes from the formation, okay, from the produced water, and usually from reduction of pressure and temperature. Okay, now we have a change in generation. Okay, CFD stands for, and what is it used? Make 3D studies of particular geometry, and you see the flow inside in detail, how the flow will go inside that geometry and what pressure do you have. And usually very useful for erosion studies, if you want to study erosion in a choke, erosion in a manifold, and also very important to see the temperature distribution in the component, okay, in a choke. For example, to detect cold spots in the choke where you might have formation of hydrates or where you might have excessive cooling, and also to calculate some other things. So it can be used for these two. Okay, so we had 10. Protect the metal with the layer of non-reacting oxide, inhibitors, or use corrosion resistant. That is not economic for long transportation distances. Separate water. If we are talking about in-well, it's very difficult to have downhole separation. Again, to separate exactly all water is extremely difficult. People have the dream to have it in subsea processing, to have that you can not inject corrosion inhibitor for the main transportation line, but you have to separate water before, but we are not there yet. Okay. Cloud point, remember wax appearance temperature. Around 4 degrees 12 bar. Okay, so really wax is, the temperature is usually much higher than hydrate. Okay, so it's if we have a waxy crude that have the tendency to, we have to, has to be addressed, because we will have probably, no matter how good insulation, we will probably have reached that temperature someplace in the pipe. What is the pour point? Pour point is the lowest temperature, and is when you take it in a bottle and then you try to turn it and it really doesn't flow. And the main problem with pour point is gelling in pipeline. Okay, if that temperature in the pipeline cools down to the pour point, you're going to have gelling, and that gelling is very difficult to start moving the fluid inside the pipe. Okay, someone is on fire, looks here. That is okay. Mixing, steering, shearing, does it help? Really break. When we have vigorous mixing, we have flow through choke, flow through this subsurface safety valve, when we have mixing of two streams from a well, that really actually forms emulsion. Okay, it's like the same effect. Remember all the time the example of the blender, that you put in the blender oil and water and you get up with this mayonnaise substance. Okay, mixing is an enemy of emulsion. Okay, so some people that want to execute, for example, subsea water separation, they say, let's do it with no choking. Okay, but yeah, so I will take that later. Okay, that's going to be a tough Only two of you got it correct. Okay, and the last one. But you need these asphaltenes to be present in the, well, you don't need it, but it's a way that they create nucleation around the wax. They nucleate, they grow around the asphaltene. Okay, so the winner is AMHM, okay, Ulfik Dudan and Kim on the third place. Okay, no presents this time also, sorry. No prizes. Okay. Yes. Well, what I was saying is that you have, okay, let's see, we have our well. Now we go to the, again, boring part of the teaching. Okay, you have here, let's say that's a very long transportation distance, 20 kilometers. Okay, so people say, why to transport the water all the way from the well to the facilities if we can just separate, put certain component, okay, that will separate and take out water. Okay, and again, the people promoting that technology say, we don't like this mixing, okay, because that creates a very stable emulsion, and then when I come here it's very difficult to separate. So let's just remove that choke, okay, and well, to control production, they say I can still control it here. Okay, I can still put a choke someplace here. Okay, and just to call to your mind that that sounds like a very nice idea, But one of the issues are, first I want to be able to control, you have a network, okay, and each well is producing and competing against each other. So you have a weak well close to a strong well, so you want to be able to choke. You okay? Yeah, okay. Otherwise I have to do Heimlich maneuver or something. So yeah, so again, so first is that each well is different. Okay, so you want to be able to choke them separately, but when you choke here, remember all the pressure drop is going to happen here. So yeah, that means that the pressure, operating pressure of the pipe will be much higher than in this case. Okay, if I put the choke here, the pressure reduces, and then the pressure in the whole pipe is low. If the pressure in the pipe is low, that means that the thickness can be smaller. Okay, that means that the pipe can be cheaper. If now I choke here, that means that everything upstream is operating at high pressure. That means that the pipe thickness has to be bigger. Okay, that means it has to be more expensive. Okay, so there are some things, not all the time every idea it's like fabulous, we have to go for it. There are sometimes some things that are completely non-related to the technology that make it a bit difficult to apply. Okay, so you have to, that tells you just that every idea has multiple sides. Okay, so now it's I think I didn't show this diagram last class. So where is each problem acting? Okay, now we went through all problems, more or less, the most important. Okay, and basically asphaltenes we can have all the way from the reservoir to the process. Okay, scale also, scaling in the near wellbore formation, it's also an issue. And sometimes they do stimulation, they inject some chemicals to try to clear or to try to dissolve the scale that is formed in the reservoir. And actually it can happen also in the process. Hydrate usually inside the well, it still keeps very warm. Okay, so we have it from the last part of the well, okay, the shallower part of the well, all the way to the process. Wax more or less the same. Emulsion, actually we can have it any place where we have the mixture. Okay, so it can be inside the well and all the way to the process. In the process it can cause very big problems in this first stage separator. That we didn't talk too much, but that's flow-induced vibrations. Okay, and actually they don't happen in the well, but they happen in manifolds, they happen in pipelines, they happen in jumpers. Okay, not so much in the process. Corrosion, every time when I have contact with the water and the wall, so from the well to the end of the process. The slugging, usually I can have slugging inside the well. Okay, I can have, if my well, if you see the profile of my well, if it's a horizontal well and then I have some undulating profile, okay, and here I'm producing from the reservoir. Because of that I might have also accumulation of liquid, okay, and I have some slugging inside the well. And all the way pipelines, usually in the process we try to put something. Remember, the process like very stable things. Okay, process likes this behavior with time. If I start going like that to the process, usually doesn't work. The guy is just going to give up and quit. And erosion, again, we can have erosion in the well or all the way even to the process. Okay, another comment that I want to highlight is that maybe that later. Some other issues that we are not going to discuss here, but that you have to know that they exist, issues to consider, are bacteria. Okay, we have also some organisms that like to live and make our life a bit more difficult. So for that I have to inject sometimes biocide. Then I have for against corrosion, if you remember, we have two things. One of them is the oxygen and the other thing is the H2S. Okay, so we have what we call scavengers, okay, for oxygen and H2S, sorry, it's not H2O, but it's H2S sequestration. That's to mitigate corrosion. That's corrosion. Some other things that we have are antifoamers. Okay, and that happens when I have liquid. Okay, all of you know what foam is, but liquid plus gas. Okay, that creates this kind of foam or bubbly structure, and that's very difficult to separate. Then we have DRA, that they are drag reducing agents. Okay, that they try to reduce the delta P in the pipe. Okay, and there are different mechanisms. Okay, and those are other things to consider that we are not going to discuss. So let's maybe we can take a break now, 15 minutes, and come back for next hour. Okay. So where are we? So that's it's just to mention that it exists. We will see now the consequences that it has on the field planning phase and also during the operation phase. But usually they are, we cope with many of these flow assurance issues with just production chemicals, what we call production chemicals. And really for, a big thing with production chemicals is the cost, okay? There are different compounds, they operate in a different way, also they have different levels of cost. So that's one main factor that one has to look into, the cost. And compatibility. Usually you have, for example, a scale inhibitor and then you have a corrosion inhibitor, and maybe they react somehow that they cause an even worse problem, some deposition of solids, some formation of compounds, undesired compounds that you want. So compatibility is a big issue that you all the time have to take care when you design your production chemicals. And also here, remember that we also have some other things or other strange chemicals coming from the reservoir that they are used basically in EOR processes. We have some polymers. We have also some nanoparticles. And we have some also that they change the properties to improve recovery, okay, to make the front more uniform. So you have to also make sure, because you're putting, if you see now, it's kind of a lot of things that you're injecting into the well, okay, a lot of chemicals, a lot of treatment. So you have to be sure that all of them are compatible and you don't have any surprises. And then another thing that one has to take care of is also the environmental impact. And so here many of the production chemicals will end up in the liquid, okay, in the liquid phase. Mainly most of them act, if you see, they act on the liquid phase, will end up in the liquid phase, and that's basically in the oil, are also in the water, okay. And in oil might not be such a big problem because oil is not released to the environment, but it might be a problem that you have certain compound that you send it to the refinery and then you create a plug in the refinery, okay. That thing deposits later, that compound deposits later in the refinery, and for example plugs a heat exchanger, a pump, and then they're going to go back at you and raise you hell. What did you put in that oil, okay? So it's not that it's problem free, it's better for the environment, but you have to be careful with the downstream user of that oil, of that crude, okay, because it can cause some problems. And water, usually, so let's maybe put it to the left. Okay, so here we say that's better for the environment, but bad for refinery, okay, or for any downstream process that will use our oil. And water, basically, remember, we can have injection, that in that case is also not important, not so much, all the chemicals that we dispose, but we can have also disposal to the sea, and in that case is a big issue. We have to be careful, and we have to be under certain limits, under certain concentrations, under the allowable concentrations. Okay, and we are not going to go into that, but there is an entity that regulates how much you can dump and what kind of components you can dump to the sea and what is the allowable concentration. Yeah, just to give you an example of the magnitude, so that's a field called Ivarosen. It's from the Noshke, now Aker BP, and they will have a platform as jacket where they are going to drill most of the reservoir, the main reservoir, Ivarosen, and that one is called West Cable, I think. And then they are going to have far away 14 kilometers, so it's very unfeasible to drill a well from the platform there. They are going to drill one well from this reservoir called Hans, and actually that's going to be your fourth exercise. Is going to be on flow assurance studies for this well. Okay, but the main point is that this field, they have a document called, you can find it on the web, Ivarosen, it's consequence utretning, and that's what's utretning? Utretning. It's like it's like consequence study, okay? That you deliver part of the you deliver as part of the PDO. And there you can find, I was looking last week through it, and you can find actually all the chemicals that they are using, and all the concentrations that they are using, and what they expect it will end up in the, more or less, in the environment. Okay, so that's a table from that report, and that is scale. Okay, so they inject the scale in the produced water. And remember, here actually we have the wells go directly to the platform. Okay, so you don't have long transportation distances. So really, all of these chemicals, most of them, they are to avoid these flow assurance problems in the processing plant. Okay, but you see the amount, how many of them you have. Scale in the produced water, scale in the injection water. You have corrosion inhibitor. You have emulsion breaker. You have this foam. Defoamer, you have flocculant, you have wax inhibitor, biocide, this oxygen scavenger, H2S scavenger, and MEG. And MEG probably will be used for that particular well, okay, because it's far away, and you have probably the possibility of formation of hydrate in that line. Okay, but you see the amount of things that they inject and the typical concentrations. So scale, corrosion, that's wax, just to give you some translation, and you have to quality control, that's flocculant, it's almost the same. Then you have this is foam, defoamer. And this hammer, that's inhibitor. Yep. Okay, so another thing I want you to check to see from this table is the way all of them are injected. Okay, And you see some of them are continuous, some of them are every once in a while with certain frequency, and some of them are has required. Okay, so you see continuous, then you have periodic, that I do it every certain time, and then I also can have has required. Okay, and as I told you, for example, if you have a hydrate formation in a line and the pressure, you know that the temperature will go inside the hydrate formation region, then you have to inject continuously MEG to avoid the formation of hydrates in the line. Okay, but if for some reason, for example, doesn't go inside, okay, but it goes just up to here, in that case you don't have to inject during operation. But you have to be careful that when you stop production, that fluid is going to cool down, and then probably it's going to go inside the hydrate formation region, okay, during cool down, during shutdown, and that's where you have this has required. Okay, so that's specifically for example, it's also used to remove scale deposit, for example, or also to during shutdown periods. Okay, like for example wax, that's hydrate and wax. Okay, that wax for due to the gelling. If you have a problem that you could have gelling, so then you have to inject this pour point depressant to be sure that it won't make almost like a solid in the pipe, but it will still be allowed to flow after some time. And the hydrate also the same idea. Okay, and the last comment on this so remember, some of these chemicals, they are not injecting all the time, they are every once in a while. For example, if you see that you are going to allow scale to deposit, and then you're going to remove it every once in a while, or you can also inject it very continuously. And another thing is most of these chemicals are not recovered, okay? So what we call reclaimed. Methanol, MEG, or methanol or TEG, there are exceptions. Okay, and I'm not sure, it's not exactly, I didn't find any information. I did a search last week trying to see if there is any other recovery how do you say facility for another kind of chemical, and I didn't find. So, but I'm not exactly sure, but most of them, they are just dumped to the sea. Okay, so you have to be sure that the concentration doesn't exceed the allowable, and also that means that it's very, very expensive. That's except. So I encourage you, if you have some free time, or if you come someone from Statoil to give you a lecture on flow assurance, on scale, you ask also the question, how do we recover that inhibitor? Usually many of them are dumped to the sea, but as regulations become stricter and stricter, sometimes you cannot honor that, and you have to have some reclaiming mechanism. Okay, but that I'm not sure. I know MEG exists, but the rest, I don't know much. For those of you who want to, who have a chemical background and want to dwell more into production chemicals, you can go and check this book. It's from a professor in Stavanger, and can really complement your education. So let's make kind of a summary table. Okay, from the issues, flow assurance issue, and the main consequence and then we are going to say just corrective measures, okay, that you are usually applied. So let's start first by say slugging, for example. Okay, the main consequence, if we have, you remember that we had last class, we have these three things, that one of them was increased delta P, flow restriction, and blockage. Then we have integrity problems. And then the last thing we had was loss in functionality. Okay. So slugging really can cause these three things. Okay. And the corrective measures, usually they are in the design phase. I try to select correct selection of pipe diameter. Also the selection of the trajectory of the pipe. If there is a part, you see that there are a place where you have too many valleys, that you might have accumulation, so the trajectory of the pipeline. Or also if you have to filling or digging the seabed, okay, the seabed. Okay, if you see that there is a place where you can fill, just to put the pipe that it won't have to go down and up again, or some place that you have to dig to avoid that it will go up and down again. What else? Okay, and then you have some control scheme, but usually we want to avoid to have slugging at all. If slugging is a big issue, we avoid having it. Or in the case of Snow White, if we are still expecting big slugs, then we have to use a slug catcher. Okay, that is just like a very long separator that can take very big batches of liquid that comes at once. If we see we cannot avoid it, then we have to make something on our processing facility, and that is the first stage separator. In that case will be special. Okay, then let's go down to the next issue, that is wax. And wax really can cause typically number 1 and number 2, okay, blockage, and also increased delta P, sorry, yeah, mainly number 1. Okay, and the corrective measures, that's going to affect the insulation design. If the distance is very short, I can also influence the heat tracing, if I need heat tracing or not. Then it can, really important wax is the pigging loop. So it has a very big impact on the architecture of my production system. So that will be a requirement of pigging loop. Okay, and also chemical inhibitor. Okay, and chemical inhibitor takes two things: the amounts to inject and also the distribution system. Okay, we have to take those chemicals down to the place where you need it. Okay, if you see they're going to happen in that pipe that we put before, we have to put a line from where I have the chemicals all the way to the well. Okay, and we will go back to it now at the end of the class. I will try to give you some drawings that I brought. but that one is affecting what kind of that you have to have it in your distribution system to inject this inhibitor, this chemical. I think that's okay. I think that's all. Then we have hydrate. Okay, that can affect 1 or can also affect 3, a bit the functionality depending where it is formed. And here is affecting more or less the same thing as wax. Okay, insulation design, heat tracing, not pigging loop. Okay, that doesn't affect the chemical inhibitor, the amounts, and the distribution system. Running out of space already. Okay, scale basically can lead to also again number 1. You see number 1 is a repeating problem, increased pressure drop and loss of functionality, number 3. And again the same thing, chemical inhibitor, and here we have there is a slight difference that the distribution system usually of wax and hydrate, they are on the wellhead. Okay, they don't have to go inside the well, but usually scale I have to have access because also occurs inside the wellbore, okay, in the tubing. So the kind of the consequence is the same, but here is in well injection. Okay, and if I need to have a continuous scale injection, then I have to put something that will go down and along the tubing, and it will be injected where it is exactly required. Let's see, scale, then we have erosion. And erosion basically is causing number 2 and number 3. And basically erosion is the pipe size and diameter. Also flow line dimensioning, component dimensioning, okay. Yes, erosion, and then the last one that I had here is well, corrosion. Okay, corrosion is basically integrity, and yeah, basically the main thing is integrity. And again we have this chemical inhibitor, and that also is frequently injected in the well if the well is not made of corrosion resistant alloy. Let's see. Okay, and emulsion, that's the last one we are going to write on this table. Emulsion also number 1, and again chemical inhibitor, chemical substance, and that also might be done in well. Okay. Another comment, I think I have here a figure, let's see if I have it, okay, that you have to be careful that not only the temperature, so the temperature along the flow line, okay, along the main production line, temperature and pressure, the evolution, also on the specific components, but also on what we call dead leg. Okay, dead legs are geometries or places where there is no flow during normal operations. Okay, and they might cool down and they might reach some temperatures that they are where you will have some flow assurance problems. Okay, so like in that case, you have a manifold that's taken from a presentation at the UTC conference last year, I think. Yep. And there you have this arrangement where all wells they go and discharge to the same manifold, and then you have the fluid going to the left, and probably that pipe is part of the peeing loop. Okay, but that part is going to, for example, this part is going to cool down. Okay, and when it cools down, you can reach, you still have presence of hydrocarbons, you still have presence of water, but then the temperature will go down. And if that's the case, you will have potentially problems of hydrate formation or wax formation in that particular place in the pipe, called dead leg. So the design of dead legs, it's also design and study of flow assurance problems in dead legs is also important. Okay, not only kind of the flowing system where the fluid is circulating through, but also fluids where the fluid is not circulating through. That you know there you're going to get significant cooling. So some options to do it, you can have heat tracing, or you can also have a better insulation for that particular part to compensate for the fact that you won't have all the time fluid replacement of fluid. Okay, so that's one thing I wanted to say. Okay, and then we go so in the design phase of the field, considerations during the design phase of the field or during field development. Okay, during the early studies, okay, where we have many development options, okay, the main thing is to detect potential, what we call showstoppers. Okay, some potential things that can cause our system not to produce as expected, and usually these things are the main three bad guys that are slugging, wax, and hydrate. Okay, to try to evaluate for each alternative, if I have, for example, subsea system with long transportation distance, you have more than 30 kilometers, well, probably their wax and hydrate are going to be a big issue. I have to put two lines, and that will modify significantly the NPV of my project, okay, or the injection of inhibitor. Also, slugging, as I told you, the trajectory of the pipe, and there you do it very shallow, but you do it for all development options. Then we have the feed phase. Okay, so what was feed? That will go maybe in the exam, feed. Okay, we leave it for homework. Okay, it stands for something, but it's after you have a specific alternative selected. Then you have to do an in detail study, and basically here is that I develop my hydrate management plan, okay, my wax management plan, make the detail pipeline design. Yeah, do you know what do you remember?
Front-end engineer design.
Yes, front-end engineering design. Okay, where we are kind of going down, narrowing down in every small detail of the alternative that we think is the most appropriate. Detailed pipeline design. So here we have also the prediction of temperature, velocities, pressures in components. Okay, and that gives me, that usually is done, like I told you, using the CFD tool, and that usually gives me is for dead legs, okay, for erosion, okay, and then at the end, after I have cold spots, if there are any particular cold spots, okay, and you also have flow-induced vibration that you want to analyze the structure if you have any fatigue due to slugging in the subsea components. And then comes the last part, that is APC, stands for no? That happens, okay, you see it, it was not so far, not so long ago, but it sounds like very long ago. Engineering, procurement, and construction. Okay, where you also make some analysis, but basically you have defined the basis of what you need here, the basis of the geometry. Maybe here we have to make some major revision, we have to address some small things, but the main and the more detailed flow assurance its effect, we are going to consider it during the feed. Now, for which kind of tools that we use for the analysis. Okay, remember, basically we have multi-phase flow simulators, and also transient flow simulators. Okay, and basically here we can use HYSYS, we can use also GAP, okay, we can use PipeSim, but if we want a more detailed study, we want to use Olga, we want to use LEDA, or we want to use Flow Manager. And basically the main point is to predict pressure, temperature, and also volume fraction of oil, gas, and water along the pipe for different times. Okay, and then detect if I will go inside the hydrate region, if I will go inside the wax region, if I will have slugging, if I what kind of pressure and temperature is really the first step for many other things. Okay, so that's one tool that we use. Then we use we need, for all of that, we need PVT analysis, and this is basically split into two phases. One of them is the lab test. Okay, we want to test first what components do I have in my oil, and also make tests of what is the volumetric behavior of that oil. Okay, some depletion experiments, and I want to develop an equation of state that represents with an accuracy, acceptable accuracy, my fluid. Because once I have that equation of state, I can use it in all the other things. I can use it in my simulator, I can use it in CFD, etc. And also here I have some particular tests that I make for wax, okay, that especially because of the wax appearance temperature, the hydrate, I might make some test on hydrate, not so common. Then I have precipitation of scale, if it's prone to deposit scale, to precipitate scale. Also emulsion of the produced water and the oil, if I have it, to see if that tend to create emulsion. Okay, some also lab tests are sometimes done to predict erosion rates. Okay, and the last that I will mention for now is CFD, okay, computational fluid dynamics, and also FEA, that is called finite element analysis. This is made to calculate velocity in all directions, pressure, and even temperature in a 3D domain. Okay, and that's to calculate displacements and stresses in a 3D geometry. Okay, that later I can use to predict fatigue, to predict thermal stresses, slugging stresses, dynamic stresses, etc. So I think, and then the last tool we have is the standards. Okay, we have some standards that give kind of a cookbook what to do when I have to address certain issues, to design cookbook, or also called recommended practice. Okay. Yes, that clear? Okay. So now let's go to talk a bit about this chemical. Okay, so this delivery system for production chemicals. Okay, and for that you can pass it there and there. Okay, and I'm just going to show you here a figure from a field, but it can in reality be any field. That's Njord, and that's just here offshore Trondheim. And the way it is, I think we have discussed, maybe, I'm not sure if we discussed it before, but it's a floating semi-sub. All of you got the paper? Yeah? Was there enough? Okay. So each well produces separately. You have no network, but actually each one of them has their own production riser floating there. The semi-sub is located exactly on top of the wells, such that if I need to make any intervention, you see that it has the drilling tower, so you can go and make intervention on the wells. But if you see here, there are two things that are kind of overlooked. We have here two small modules that also have their pipe or their cable coming from the platform. Yeah, and these are what we call the they can be called CDU, control distribution unit, okay, or SDU, subsea distribution, and that's the component or the main component that serves all of these chemicals and other things we will see right away to each one of the wells. And the main cable that you have, or the main thing that you have from the semi-sub going down to these modules, is what we call, how is it called? Umbilical? That name is the first time you hear it? No? Umbilical? Is it really the first time you hear it? No? Maybe you had it in some Statoil presentation. Okay, umbilical, and the umbilical looks something like that. I think I have a picture. Okay, and it's actually a bundle. Okay, it's a cable, it's like a cable, a mixture of a cable and a pipe. I think the umbilical is that joins the baby with the mother. Okay, that's what you call the umbilical. Okay, so that's why this supposed to give everything that the well needs to be healthy and grow and get old, etc. Okay, so it's a bundle of pipes that carry the main things that the well needs. So don't mind too much about the structure, okay, but it has a sheet that is protective. It has also insulation, some plastic sheet, and then inside has what really matters. Okay, so first you have the power cables. Okay, you have some valves that you need to they need power, that they are electrically activated. Then you have communication. You have sensors of pressure, temperature, flow meter, sand detector, that they are there, so you have to get the signal from them. Then you have these pipes that they carry the hydraulic fluid. Remember that all of these big valves, like the master valve, wing valve, they are moved with fluid. Okay, and also the subsurface safety valve, high pressure fluid. So that fluid has to go at high pressure. And remember also we have a low pressure. All of these pistons, when we move them, okay, like for example you have here the actuator. That I think we didn't discuss that, but we have our gate valve. Again we have okay, I think I made that drawing before, that part is going just up and down, okay, either blocking the flow of fluid. When it's in line, it allows the fluid to go, or it goes up, it blocks it when that part is in front of these two. Okay, and that part is activated by something like this, another piston, and here I have a high pressure fluid, hydraulic fluid, and here comes low pressure. I have to, that part is filled with some oil, okay, some hydraulic fluid, that if I want to open that valve, that one has to be, the LP has to be completely empty, okay, so that goes down, moves down at the fully closed position. Okay, it will be like that. But then when I want to open it, I have to put high pressure fluid on that side, and then the piston will move up, and then I have to drain from the low pressure side, from the low pressure hydraulics. Yep. So those lines, that's why I need some high pressure and low pressure. So one is the going to the actuator and coming back from the actuator. And then I have MEG. Okay, so here they call hydraulic control. That's what I call hydraulic control, low pressure and high pressure, and injection of chemicals. Okay, hydrate inhibitor, MEG. Okay, corrosion inhibitor, scale, etc. And there you have some other things like that are these things that are just fillers that are just keeping the integrity of the cables, keeping them in the same position. So communications, power cable, um, injection of chemicals and hydraulic lines to move the actuators of the valves. That's everything usually what the umbilical has. You have now some companies that are trying to push that also you have the production line as part of the umbilical, but these are more expensive and they are not so spread. Instead of having two lines, one production and one umbilical on the side, you will have all of them in one, but that's not spread so much subsea. Okay, and here I think we have the same. So here you have this high pressure, low pressure. Okay, and they have to be in a different pipe. Okay, the high pressure cannot be the same if you are going on that direction towards the well and you're coming back from the well. You have to have two separate lines in the umbilical. Okay, now if you go to the drawing that you have, and I'm going to, not to cut the explanation, I'm going to discuss it and then we take a break. Okay, I won't forget about the break, I promise. Okay, so let's see, that's what you have here on the left. Let me make it smaller. What you have on that part is what we call the Christmas tree. So I recommend you to take the pen and start making all the comments. Okay, so that's what I call the Christmas tree. So all of that is positioned in this module. If I'm talking about a satellite well, is positioned in this block, a big block of big dimensions, big weight, that is called the Christmas tree. And can you recognize from here some of the elements that we have talked before? Okay, what is SCSSV? Subsurface safety valve, but SC is surface control. Okay, surface control, subsurface safety valve. Then, so the thick line is the main production line. Okay, that box that you have here, that's actually the tubing hanger. That's what keeps that is what is holding the whole weight of the tubing, and also that's what is making the seal such that nothing that is above can go inside the wellbore. Okay, that only you have communication on the wellbore from these lines. Okay, and they have a hole. So that's a tubing hanger, and it's a block, and it's actually, if you see it from the front, it's like a disc, or you see it from the side, it's like a disc type structure where you have holes for the different things you want to send to the well. Okay, you have, for example, the connection to the annulus, and if let's make it so in our diagram of a well. Okay, if we have our well here, if you remember, we had something like that. Okay, so the tubing hanger will actually be that packer that I'm painting here, and the annulus, you will have a connector going through there. Okay, and then you put there your master valve, etc. So that's the hanger, and I tried to find a picture, I didn't find, maybe I will paste it later. But after that, you continue. Let's take the main production line, and we find that valve that is called, the first valve we meet after the tubing hanger is called P production master valve. Okay, and if it's empty, okay, if it's not filled, it means that it's normally open. Okay, non-filled valves mean normally open. If you see that valve that they have dark color, that means that they are normally closed. Okay? The square on the top indicates that is hydraulically activated or remotely activated. You will see that now we will see some valves that actually you have to send something, typically an ROV, a robot, to open it or close. And these are, and also one more thing, these are on and off. On off. They cannot be used for control. They cannot be in an intermediate position. Why? Because otherwise you destroy the seal surface and you destroy the valve. Then it doesn't, and that's very important. If that valve starts to leak, you have a problem, and that's a very huge safety problem. Okay, you have to stop production, shut down your well, and replace the component. Okay, then you have TTPT. What does that mean? Temperature transducer, pressure transducer. Okay, then let's continue with the main flow. We have PWV. What that stands for? Production wing valve. Okay, and if you see the same type, remotely activated, it's open, and then you have again another pressure and temperature. Now you see that you have again another block, and through that block you have many connectors. It's basically the same idea, has a tubing hanger, that you have just one big connector where you have multiple. It's called a multi-bore connector. And I think I pull a picture how it looks like. Something like that. Okay, a multi-bore connector. Let's put a star and put it below.
Excuse me, what does it say on the temperature thing?
Transducer?
Transducer.
Yeah, sorry, let me make it nicer. Yep, better. Well, not really. Okay, yeah, so we now pressure temperature the same. SD stands for. So now, if you see, now we are leaving kind of the Christmas tree module, and we are entering that module that is called the production control module. And it is called production control because basically it has the choke. Okay, the choke is the main control element for the well, so that's the production control module. Okay, and there what do we have? Let's continue following the flow. The main production line, we have SD, that stands for sand detector. MPM stands for multi-phase meter. PCV, production choke valve or production control valve. Okay, and then I leave through there and connect to something else. Okay. Production control valve. So just okay, so if the well are the wells are in templates, okay, then you will have, remember, in a template, all wells we have usually here in the North Sea, we have usually 4, okay, 4 wells, and we have here in the center a manifold, okay, that takes, I think I showed you that picture, let me bring it here maybe for clarity. I think we have, if you didn't forget, long time ago, okay, we had every well was positioned here, and then you had a connector that takes it directly to the manifold, okay. So if that's the case, that will be directly connected to the manifold, and in that manifold, that multi-bore connector is that connector that you see, very small. I think during the class I said, but that connector that has, you see all the chemical lines, all the hydraulic lines, all the communication lines, power lines, they go through that connector, okay. I call it type connector.
What is the function of pressure, temperature, transducers?
Well, for many reasons, but it's basically you want to know what is the. If I ask you what is the wellhead pressure, remember, for us production engineers, wellhead pressure is very important, extremely important. Okay, so you have pressure, you have redundancy. That equipment will be there for maybe 10 years. Okay, so you want to have, if one gets damaged in one position, okay, you still want the other one to be working, to be functioning. Okay, temperature transducer, the same, to monitor the temperature, and also to, for example, for this, all of this flow assurance. Sand detector, if suddenly I start getting more sand than expected, I have erosion, okay, and I have to be very careful because erosion can eat up my material very quickly. Multi-phase meter, I want to know exactly how much our well is producing. Let's say that in this template I have a well that belongs to Statoil, one that belongs to Shell, one that belongs to Exxon. So I have to know exactly how much each one is producing, okay, for test. So that's a very expensive, so that is very expensive usually, and I want to get the most out of it. So if I just plug in a few meters and some redundancy, so it will hold for 15 years, 10 years, let it be, okay? I put some more, put some less, put pressure, temperature across the choke. So again, so that's the multi-bore connection, or if the wells are satellite, so just again, sorry, here you have the Christmas tree module, and just next to it you have the control module, control, production control, and that's the Christmas tree. And then you have this multi-bore connector, and there you have the distribution. Okay. If the wells are satellite, you have, each will have usually the Christmas tree, and then you have the choke module. This is sometimes called the choke, the production control, or sometimes it's also called the metering module. And then it will have this multi-bore connector to some other unit that is called, that in that case that we said before, is this CDU, okay, or SDU, subsea distribution unit. Okay, that, if you have several wells around it, like in the case of Newark, it will connect to each one of the wells to give, that's not production, okay, but that's just all the other auxiliary things that it needs to operate. So now let's go to the next, to the other things that we left here. So SCV, what does it stand for?
Surface control.
No, that's not surface. That's scale control valve. Okay, scale control valve. Okay, so that I regulate how much scale I am injecting to the well, and that is scale injection valve. And if you see, I injected just upstream the production wing valve. for this particular case. Some others, they might have a different. So here the fluid is going, the production is going on that direction, okay, from the well out, and the inhibitor is going from some other place, from the manifold or from this distribution unit towards the stream, okay. And in that case, I didn't have to, in this case, maybe scale is not an issue inside the wellbore, it's just an issue downstream. Okay, if not, remember, I will have to bring that, okay, make a hole in that tubing hanger and bring it down. Yeah, but that's not our case. Then let's see other things. This MIV stands for, just a tip, that's also for flow assurance. That's MEG, injection valve. Okay, and that's MEG, control valve. Okay, and in that case, MEG is circulating there, and I expect don't have any problems inside the wellbore again, so it's okay if I inject it downstream. Yeah. This stands for, now this one is connecting the annulus, that pipe is actually this pipe, okay, and that pipe is actually this pipe. So this is the annular master valve, annular wing valve, and that's the crossover valve. Okay, and basically I'm not producing anything through the annulus. Let's assume that here I have a packer, okay, and the annulus is completely sealed. I should have no pressure, nothing there. What happens if I start at some point monitoring pressure? The pressure goes up. These are normally closed, okay. The pressure goes up, that means that maybe I have a leakage someplace, okay. Maybe a hole in the casing, it's starting to get pressurized, that annulus. Maybe I have a leakage in the packer. So that pressure is extremely important to monitor with time, the annular pressure. Okay, and if I have some overpressure, I can try to bleed it. I open these two valves, or I open that valve and I bleed it, okay, to a area where I have lower pressure. Okay, now it became very messy, the drawing, but let's go, before going to the break, let's see how this subsea distribution unit looks like. Okay, and it's here. Okay, so you see here you have the umbilical, the main umbilical from the platform, okay, or from the facility, and that in our case of Newark will be this main pipe, okay, entering just the control distribution unit, the subsea distribution unit, okay. And you see I have all the different things that I showed you before: the scale inhibitor, hydrate inhibitor, biocide, corrosion inhibitor, wax inhibitor. We have the communications, the sensors, power, hydraulic high pressure, and hydraulic low pressure. And I'm showing here just two, because if I show all of them will be a bit messy, okay. But you see it goes to two headers. These are two headers, okay, and in that case they can go to 4 wells, okay. Here I have well 1, well 2, well 3, and well 4, okay, and I'm distributing through all of them what they need exactly: the hydrate, the scale, etc. And from here you have, depending on the case, but usually you have another umbilical that goes to each particular well. For example, I want to supply that well, then I connect with an umbilical to that one. And this has nothing to do with production, okay? Here we're looking just at the chemical distribution system. Nothing to do with production. The production goes separately. If we have production with black line, that will go separately to another manifold template, okay, and later to the pipeline that will take it to the platform. Okay, two different systems. So don't be confused when you see, because you're going to be exposed working in the oil industry to many. That's what we call a flow schematic. Okay, and you don't be confused. If you're looking, your problem is something that has to do with production, look just at the production lines, neglect everything else. And if you are looking for something in the chemical system or in the power system or in the communication system, look only at that part, okay? Because you have many layers of things falling on top of each other. And one more thing I want to say in the figure, that means this open, it means that it's manually activated. Okay, that means either by diver or in the case of Muir by ROV. Okay, that means that it's normally open. That circle that it has in the middle, that means that it's a ball valve. And they are normally open. Okay, so if I want to, for example, I want to do some kind of operation in the well, I have to send the ROV and close them manually. Yes. Any question before we take a break? That more or less clear? Here you have, if you want to see it during the break, here you have one full diagram to that's a subsea field in Brazil, okay, the Corvina field. So there you have, and you have actually all things, wax inhibitor, hydrate inhibitor, emulsifier, okay, and that also has gas lift on top. So if you want now during the break, you can take a look, and I can just explain a bit what do you see. So let's take a 15 minutes break. Yes. So now just changes in temperature and in pressure are extremely important for many things. Okay. And we have seen already how to predict pressure change. Okay. With some pressure loss model. And we went through single phase gas. I mentioned about liquid, and you know already in detail how to calculate for multi-phase, but we haven't dwelled too much on temperature. We usually, up to this point, is like we assume a profile is given, but I just want to make some comments because you will need the how to calculate temperature for the exercise. So one thing I want to call your attention first is that you can have fluid cooling due to expansion in chokes. Okay, in chokes usually delta P, P1 minus P2. Okay, and temperature 1 might be a bit similar to the temperature of the reservoir. And then you have an expansion, you have a reduction of pressure, and that can affect significantly the pressure downstream, especially if it's gas. T2 might be very different from T1, especially if mainly gas. Okay. Okay. Yeah, so if you remember the first law of the thermodynamics, something far away from your when you were in Grundschule or kindergarten. First law of thermodynamics for open systems. That means I define an open system like a box where I have, I can make a boundary, or I can make a kind of just to delimit that surface. Then I have something coming in and something coming out, and then I might have also heat coming out and work coming in and out. Yeah? If we say that's a piece of pipe, there is actually no work, just heat being lost to the environment. If that's a pump, for example, that one is negligible, but the work, the power that we are introducing to the fluid is important. So that expression was, if you remember, or if I remember correctly, Q minus W equal to mass flow of U2 plus P2 over density plus Z2 plus V2 squared over 2 minus U1 yes. Okay, that brings some memories. I'm not sure if good memories or bad memories, but memories. That should be G. Okay. Okay, and then we said to make it for, especially for chokes, okay, we can say that there is really no significant, it's a very short distance, so we can neglect the heat transfer, and we can say that the power also, there is no power because we don't have anything actually administering power to the fluid. Then we can say also that the elevation, okay, that will be Z1 and that will be Z2, really is very small, okay, so that will be more or less these two, they cancel each other. Then also V1 is relatively similar to V2, and at the end we end up that, and I'm sure maybe you remember that for chokes or for valves, that H1 is more or less equal to H2, is isenthalpic. Okay, and if you remember, H enthalpy is equal to U internal energy plus PV, right? Okay, and PV is 1 over V is 1 over density, and that's internal energy. Okay, so I just pull here just to show you more or less what, but you will do later that with HYSYS, so just to make an example, here you have, that's what is called the Mollier diagram, well, not the Mollier, but is the pressure enthalpy diagram for methane. And you have some temperature lines. So if you have, for example, temperature, that temperature that goes here is 150 degrees Celsius, okay? And if you knock it with the pressure, how much is 20 bar, for example? 2 megapascals, right? Yes? Okay, so you knock it down, then you will have, at this particular point, you will have that enthalpy, and those are the entropy lines. Don't worry about them too much, that they go entropy. For that case, for example, you will have an entropy of minus bit less than minus 8.8, okay? So it's like I pre-computed, I took methane, or either I measure it in the lab, all the properties, or I just took an equation of state and I pre-compute and put all of them in a graphical way. And you see it's kind of messy with all of these lines, but we will see just right away that it's very powerful. So for example, some of you were asking, for this Snøhvit case, what delta P did you get across the choke the first year, if you remember? I think the temperature of the reservoir we said was something like 90 Celsius, so we can assume that's T1, right? Delta P, I think you had values like 160, 70 bar, was it? Who has the computer there? Alexander, can you give us, do you have the exercise 1 open there?
Not right now. Where is it?
Can you search it? Just, let's see which one is it. Exercise 3. Okay, exactly the problem of Tanzania. The delta P, yeah, the delta P across the choke for the first year, and the wellhead pressure.
Yes,
Yeah.
sorry, I didn't quite understand.
Yeah, exercise 1,
Yes,
you have your Excel sheet where you have performed your calculations in time
yes,
of the plateau, the production profile.
yes.
Yeah. What is the pressure at the wellhead
Pressure
for
at the wellhead.
time 0 for the first moment of production? Pressure 1,
That's one, right?
pressure, wellhead pressure
Wellhead pressure is 343 bars.
43 bar. Okay, and the temperature, I think we said the temperature, did we mention the temperature of the reservoir someplace?
Initial reservoir temperature was
Temperature.
70 degrees.
70?
Yeah.
Okay. And what is the delta P of the choke you get for that year?
The delta P for the choke is 267
Bar. Okay. And then we just divide by 10 to get megapascal. So let's locate that point. Okay, the mixture is not only methane. Okay, it has many other components, and probably you have condensation. So for that, if you want to get a very accurate estimate, just go and use an equation of state. But if we assume maybe it's 90% methane, 92%, we can at least use this diagram for the first approximation. So let's locate the point that we have 70. Where is 70? 50. So that's 50, 60, 70, 80, 90, 100. So 70 is that line, 70 degrees Celsius. And then we have to locate the point upstream the choke on this diagram. So the point is 34.3. 34.3, that's 20. 30 will be someplace here, right? So that's 20, 30, and 40 megapascal. So it will be someplace here in between, and you knock it with that line. So that will be, well, maybe a bit less. That will be 0.1. Okay? Then we have to apply a delta P of 26. So that means that pressure 2, it's how much? 34.3 minus 26.7. What is the pressure downstream the choke? The pressure of the template?
The pressure at the template is
77 bar, or 7,7.7 megapascals. Okay, and I locate that 0.7, 2, 3, 4, 5, 6, 7. Okay, 7.7. Okay, now that point, so that point will be someplace in that line. Okay, and I know the thermodynamic process across the choke is isenthalpic. Okay, that means that the h of that point should be equal to the h. Okay, not h in years, but the h in enthalpy. Okay, so those two should be the same. So it goes vertically during the expansion up to that point, and there you see what temperature reduction you got. Okay, the first one was 70, and now this temperature will be like 15, more or less like 15 degrees Celsius. Okay, so you have a significant cooling in the during the expansion in the choke. Okay, and that's going to be part of exercise 4. You'll have to use HYSYS first to determine what will be the pressure downstream the choke. We will do it for SNUBIT, and then that temperature you will use it to perform temperature calculations along the pipe and see if you go inside the hydrate region. Okay, usually the presence of liquid makes that temperature won't go down that much. Okay, the presence of liquid helps to cool a bit so the increase in temperature won't be so high. Okay, just to make you aware of that, every time we have expansion, we have cooling, usually with gas, and also that cooling, that's what I told you, you can cause that the pressure reduces very dramatically and you have scale. You have formation of scale. Okay, so now let's look again at the equation, okay, the full equation, the energy equation. Okay, and if we put it in differential form, okay, we can use it now. We're going to use like temperature drop in pipe, okay, or in conduits. That's useful for the tubing, that's useful for flow line. So we can use, in a pipe usually we don't have any power, we don't have any work going to the, and we can put that in differential form saying dq equal to mass flow that remains constant unless we have a transient. So here we have dH plus that will be dz g times v dv, and that's all, right? And then we divide by dl, okay, by a small section of a pipe. Now we are making our analysis on a very small pipe section, and at the end you end up with dq dl m dh dl plus dz dl g plus v dv dl. Okay, so what is that Z is the elevation, okay, the change in elevation between the point upstream and the point downstream. Okay, so that will be Z and that will be L. So really is the sine of this angle, right? So dz dl, I can express it as the inclination of theta, the inclination of the pipe. Okay, so that will be, just save time. Did you see that deduction in some other course of this temperature equation? No? Okay. So now the next thing I will, so that's something that depends on the geometry of the pipe. That's something that depends, that's a constant. That's something that depends, dH depends, is a thermodynamic property. So I need some EOS or some fluid model to predict how H will be a function of, for example, pressure and temperature. Okay, I need something like that. And we will see later, we are going to propose a very simple model for liquids. Then we have that part which is the expansion, how much the velocity changes from 1 to 2. And as you can imagine, really it's not much if you think about liquid, okay? You have no much expansion. If you talk about gas, there is significant change because the pressure might change. So that's a function of dP dL in a way, okay? So if you have a significant expansion pressure drop in a pipe segment, that might be very important. But now let's look at this guy more in detail, the heat transfer, and that's basically the heat loss that it has with the environment. And if we see any pipe, the cross section the cross section of a pipe segment. Okay, if we say it's in the well, or if it's, so we first have some temperature of the fluid. Okay, usually that temperature of the fluid is different from the temperature of the wall of the. Then you have a thickness of metal. That's, for example, if we're saying a pipe. And then we have, for example, a big insulation layer, insulation material. Okay, then we have a very thin layer of protective coat. I forgot to bring it. I have one in my office, but maybe next class. So that's protective layer. And then we have just the C. Okay, C. And then we have here some temperature, that is temperature ambient. And there will be heat transfer between the fluid and the ambient through all of those layers. And the equivalent, if you think about electricity, that is, this T is like a voltage difference, and you have some current that is going through it, and the current will depend on the resistance. The current is like the heat flow, and the resistance is all these layers you have in between. Okay, for wells it becomes a bit more complex, because you have, well, you might have an annular section, you might have again cement, okay, then you might have a formation, okay, and if you have the pipe, is instead of being open to the sea, if it's buried, okay, then you have soil, and then you have again seabed. But basically the approach that we use, and I think maybe you saw it in some course in heat transfer, is that the for example, in solids, okay, one has conduction, and the conduction, the expression of the conduction is equal to 2 pi L, the length of the pipe, times K, the conductivity of the material, times T1 minus T2. Okay, T1 is the temperature at the inner, that will be 1, and that will be 2, and here you have the ln of R2 divided by R1. Okay, I think you have seen those expressions before. And that's what happens, for example, in wall pipes, pipe walls. Pipe walls. That's what happens through insulation material. That's what happens in soil usually. Okay, everything that I don't have any movement. And when I have in liquids, I have what we call convection, and there are two types of convection. One of them is free and forced convection. Okay, and basically here the Q is equal to 2 pi R L times times H times T1 minus T2. Okay, if I have, for example, I have, that will be T1, and here I have T2, an ambient that is at a certain temperature. I use that expression to calculate the heat. Okay, 2 pi R is the perimeter, and length is just the dimension. So if we have a system that is made like that of multiple layers, we can say the heat will be the same for each layer. Okay, and we have an expression for the heat in each segment. Okay, we have one that is through in the internal part of the pipe, one that is through conduction, insulation, conduction, and then the sea. So I can start writing, for example, so let's first name that. Oh, we already finished. Do I have to make the demonstration, or do you accept it? You basically, what we try to say is that T of the fluid minus the T of the wall is equal to Q divided by that coefficient, okay? But I want to make my calculations by length, so that will be, so here I have 2 pi L K ln R2 over R1. Okay, and I do the same for, sorry, that's first I should have, so first I have convection, then I have conduction, then I have conduction, conduction, and convection. Okay, so I do the same for every layer. So here it shouldn't be like that, but it should be okay, will be 2 pi R L Q and H, okay, H internal. Then I have T wall in and minus T wall out, and here I have conduction, and that will be Q over 2, sorry, over 2 pi L K ln R2 over R1. Okay, and then I can do that for every layer, convection, conduction, 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 convection. Okay, and at the end I can sum all of those expressions. Okay, so when I sum them, that term is exactly the same as that, but with negative term, so they cancel out. And at the end I obtain that I have T of the fluid minus T of the ambient, okay, is equal to Q, the total heat loss, multiplied by a big sum of things that you have here, convection, conduction 1, conduction 2, conduction 3, and then convection again. And we will see next class that you can define a heat transfer, an overall heat transfer coefficient that expresses the resistance of all of these layers. Okay? And that, so then I have an expression of the heat, then I can use that expression inside this equation, and with that equation I can go and calculate the temperature along the pipe. Okay, we will see later, next class we will just continue briefly how to do it. Okay, so any question before we close? No? Okay, flow assurance, remember to read the chapter, and chemical distribution system, and starting with temperature, and I will hopefully publish the next exercise today. Okay, so you can start working on it. See you on Thursday.